Okay, so some time ago we were approached by the team from Italian Institute of Technology, and they basically wanted to try array chip, S40 chip for stereo vision algorithms applications. So, and before, I noticed that someone asked Greg, how, why people would prefer this chip to some other solution. And in this particular case, the reason why they would try to use our chip was the desperation. All the other solutions just didn't work. They were not happy with the results they had before. The team from Italian Institute of Technology. So basically they were building the robot, mobile robot, which is supposed to survive on a battery, and anything more than 1 watt of the power consumption was not just acceptable for them, because it's supposed to be remote mobile robot, probably swimming under the water. So low power consumption was very important for them. From the other side, they needed some kind of supercomputing power, because the algorithm, and I'll show you later, is pretty CPU consuming nature. So it's supposed to be low power, and same time it's supposed to be high performance machine. And the algorithm is not the kind of rocket science. It's very simplistic. I'd say it's rather opposite to rocket science. I'll show you the formula. But you have to do this kind of calculation a lot. So this is very, I've got a feeling, I had a feeling that this is very good match for our chip. Although they wanted to implement everything ourselves initially, and they asked us to teach them how to program this chip, because chip is not very usual. It takes a little bit different skills, skill set from you to programming than the programming the single CPU machines. It's different. And figure out that if I will show them some simple techniques how to program this chip, most likely they wouldn't do the good job of programming this chip. So I decided to combine teaching them how to program this chip and implement the algorithm myself and show them what I did and explain them why I did it this way. So I decided to implement the algorithm myself. And actually implementation didn't took long, probably take 1 working week to get it working initially. Then optimization took a little bit longer, because you had to balance the load of the chips. You have to rethink a pretty simple thing multiple times until you figure out the proper and simple way it should work. So basically the idea of this stereo vision algorithm is to take 2 stereo frames, left and right, and then based on the intensity of the pixel, and this is black and white frames, calculate or estimate the remoteness of each pixel of the scene, how far it's from you. So basically you have, this is the left and right input, and this is the output. And brighter pixels means closer pixel or point of the object to you. So the lamp is the closest to you, the head is a little bit remotely from you, and etc. So this is the very classic example. It's like a Lena picture for the JPEG decoding, the girl from the Playboy, but well, the picture is very decent. It's not very Playboyish, but initially it was took from Playboy. But you know the story. So this is very academical example. And the algorithm is very, like I mentioned to you, it's opposite to rocket science. It's very simplistic. So basically you have to you have to estimate the distance to every point of the scene using the idea of binocular vision. When the position of the same point of the scene is shifted more or less for the left and right point of view, depending on this point's remoteness. So for the closer points are shifted more relatively on the left and right frame, and the very remote points are not shifted at all. So it's just basically they've got the same location on the left and on the right frames. So for every point on the right frame, okay. So we basically have to find corresponding point on the left frame, and the measure of the correspondence, the way we figure out that they correspond to each other, is the sum of absolute difference of the pixels value and its neighbors. So basically we have a frame 3 by 3, and we subtract the value of the left frame. You know what? I probably will just scroll down to show. So basically we have a window around every pixel 3 by 3, so the pixel itself and 8 of its neighbor, and we subtract this 3 by 3 window from the left to the right window, and if the pattern on these 9 pixels perfectly matches, if the intensity of each pixel, corresponding pixel, absolutely the same for the right and left frames, we've got 0, and 0 means the total match. So this is how we estimate, you know, the quality of the correspondence of the points. Okay, and the idea is we do this operation, we do this sum of absolute difference for 16 different points from the right frame. So we took one point on the left frame, and then we subtract the different arrays, you know, from the 16 different points from the right frame. And then we select the point with the minimum difference, because point from the minimum difference is most likely the same, the point we're searching for. So, for example, if this point, the difference of this point and that point is the minimum, it means that most likely this is the location of the corresponding point we're searching for. And then we take the index, or the offset of this point, this is 7, at the index of the remoteness. So this is the way we figure out, you know, how far this particular point from our, you know, two left and right point of views from us. So let me see if I. Okay, and of course the size of this window could be, you know, different. I just choose to. We decided to use 3 by 3 size of the window. It could be, you know, bigger. If it's bigger, then the results are less noisy, but the resolution is worse. So we decided, and this is pretty typical case when you use the 3 by 3 window. And of course, you can use different kind of ranges. So right now we decided to use 16 different offsets. And of course it could be, you know, the range could be, you know, higher. It could be, you know, 20 or 32 different offsets, but it's scalable. The algorithm could be changed very easily. Of course, you know, we will need some extra nodes, but, you know, I believe, you know, especially with the GA144, we will afford it. We could afford it. So the algorithm, the idea is very scalable. So, so this is the brief description of the algorithm. Just, you know, trying to understand, you know, the best match from 16 candidates. And based on this, you know, brief description, we can figure out what kind of components, what kind of modules we will need to implement and put together. So first of all, of course, it's an input driver, input driver supposed to input the stream of pixel from the left and from the right camera. And well, actually the bit rate of the input is pretty high. So for the left and for the right, it's 22 megabits. So it's a lot of data. Well, kind of a lot. It's not a gigabit, but 20 megabits is pretty high bit rate. And we had to implement output driver, basically the place we output our result, our newly calculated frame. Yeah, this one. And we'll need a storage for at least 2 input pixel lines for left and for the right, because we have a 2-dimensional convolution, 3 by 3. Obviously, that we on top of the line of the pixels we are streaming currently, we have to recall the line of the pixel, 2 lines of the pixel we are calculated already, we are streamed already. So just to reuse it for the newly calculation. So we need some kind of the storage or a buffer for at least 4 input lines. And of course, we have a nodes which will calculate the difference, I mean sum of the absolute difference, and the idea is to calculate it in parallel, in 16 different nodes in parallel. This is where the power of parallelism coming. And then we have to compare the 16 results to figure out which index provides us with the minimum difference. Between the index of the minimum difference is basically the answer, what the offset of this particular point, I mean, what the remoteness of this particular point is. So, well, after several tries, we came to this topology. Well, this picture I've got this picture automatically. So we collected the data during the simulation, and then we build this SVG picture automatically. So we figure out the data connections and direction for the data connection. Also, we figure out the load of every particular nodes. And this is kind of a heat map. So in here, you can see that the busiest nodes supposed to be red, and not busy, the nodes which are not busy is supposed to be black. And you can see that normally loaded nodes supposed to be green, and I find it pretty symbolic. Green array is supposed to be green when it's programmed properly. So, okay, let me explain, the dedication of the nodes. So basically, we have input drivers on node 20 and 10, and we use FIFO nodes as a temporal storage. And then we have a chain of the SED nodes, which calculate the sum of absolute difference in parallel. And then we have four nodes to select minimum results. And I couldn't predict that the algorithm would be so fast that the single node which will select the minimum from 16 values will not keep the pace with the rest of the algorithm. But then it appears that I had to use 4 of such sorting nodes just to keep pace with the rest of the algorithm. And this memory map is very easy to estimate the balance of the algorithm, because if I will use the single node, the selecting node instead of the 4 nodes, then you will see that that node will be really busy. It could be yellow or even red, but the rest of the chain, all these SED nodes, could have a blue color. It means that we've got a bottleneck located with the node with the hottest color, which causes the underloading for the chips, which depend from it. And this is the output. Okay, the thing is, I was told that this algorithm, this chip, is supposed to interface to ARM chip. That's why we choose the nodes with the digital pins. If I implement this application myself, I would connect the cameras, the analog output of the cameras, directly to the analog nodes. Because the thing is, when they put everything together, it appears that ARM just cannot provide this chip with the data fast enough. I believe ARM was just inputting the bit bleeding the input from the ARM. In the best case was 5 times, probably more than 5 times slower than we can read and calculate. So, yeah, of course, they figure out how to estimate the performance and power consumption of the application of the real hardware, but it's quite a challenge to find out the hardware which is good enough for this chip and fast enough for this chip. This is the variation of the initial algorithm. Let me explain it a little bit to you. So you can see that it means that I'm supposed to sum together the absolute difference of the difference. But it's easy to modify the algorithm and replace the operation of the getting absolute value with the square, which is basically multiplication. And it was very interesting to me to figure out the importance of the application. Recently in the Complang force, there was some discussion about how important multiplication and is it that important or not. So I just implement the 2 versions of the algorithm, with the multiplication and without multiplication. And where is it? Okay. So this is the heat map of the algorithm based on the square, which is basically multiplication. It has a little bit different layout. The performance in the terms of the pixels per second are lower than in the previous case, obviously. And I didn't need the 4 nodes to calculate the minimum index, index of the minimum argument. So just only 2, 31 and 32 nodes which select the minimum. But the output, if you compare the quality of the output of these 2 algorithms, SED and SSD, SSD means the sum of square differences. The difference between these 2 outputs is hardly noticeable. So of course I will go with the SED solution because it's more efficient. But even if you compare the performance of the implementation with the multiplication and without multiplication, it's not dramatical. So multiplication is not that important. Of course, from the logical point of view, the multiplication is all the SSD version is doing, logically, mathematically. But in real life, you have to load data, you have to upload the data, you have to serve some data connection for your neighbors. There's a lot of small things you have to do. So altogether, it's not 10 times or 20 times worse. It's just only 2 times slower. But this is not what I care about. I care about the efficiency. And the efficiency in this case is how many pixels you can perform, you can process on a single joules. And you can see that the performance, efficiency is not that dramatic. Well, just to impress you, I use in the first line the example of the alternative solution with the efficiency. Because the team who wanted to try the S40 chip before, 1 year ago, used the chip CSX 700 to do the same thing. This is the SIMD chip, for embedded. It's a supercomputer, very powerful, and from the term of speeds, it's faster than S40. But look at the efficiency. It's 7 times less efficient. And that's why they were not happy. Because in this case, you consume 80 milliwatts, and it's pretty good for the mobile robot. And 9 watt of the power consumption is not good for the mobile robot. That's why they were searching for the alternative. And I think somewhere I have a description of what CSX 700 is. So basically, it's enhanced SIMD processor for embedded systems. So they wanted it to be efficient too. And basically, it has 2 processing arrays, and each has 96 processing elements. And each processing elements have a 32 or 64-bit floating point multiplier and 6 kilobyte of SRAM and the integer arithmetic logic. So this is the CSX 700 is very powerful processor, and I assume pretty expensive too. But still, why should I use this powerful thing if my major concern is how long will this robot survive on a single battery charge? And for the team, the guys who wanted to implement this algorithm on S40, this kind of result, this kind of consumption and performance, it just, it blown them away. They never expected. Well, actually, I predicted this kind of result to them, when I ran the algorithm on the simulator, but I think they didn't believe me. And they believed me only after they put the actual hardware together, and they measured the amperes and volts, and they've got the actual data from the chip, and only after that, they saw that this 75 milliwatts of the power consumption are real. And I believe, I have a picture. So this is the board, and this is the solar cell. And the power of the solar cell is enough to feed this application, even without the actual, charged battery. So just put it into the sun, and it will see and estimate remoteness of the scene. So, and they were really happy because it was kind of milestone for them. So if this application, this component can run on the solar cell with a size comparable to the size of the development board. So this was kind of proof of concept for them. Well, and just recently I found out that this sort of algorithm are very popular in intelligent vehicles. And of course, in intelligent vehicles, the low price and low power consumption is not that important. Come on, you get a $70,000 Mercedes or BMW. So who care about $10 or $100 computer and how much it consumes? But still, it was interesting to me just to take the 2 left and right frames from the site and processes to my algorithm and see it's working. So you can somehow. I cannot remove this. Okay, so you can see you can estimate the distance to the car, and you can do it 25 times a second. So it's pretty fast. Well, the thing is, if I had not 16, the range not 16 offsets, but 32 or 30, I could process this part better. Yes. So it's too close. And of course, there is some kind of aliasing effect when you can mix the array with the same pattern. You cannot figure out if it's close apart to each other or the same picture, for example. In here you've got the same color on a car, so it's easily to mismatch and to mistakenly think that this is the remote part of the object. It's not the part of the car. But there's other algorithm which is supposed to run together with this algorithm. And well, honestly, I wasn't after the algorithm itself. I just wanted to implement the known algorithm on this particular architecture and see how good it will be. What kind of performance and what kind of efficiency it will provide me with. So of course it could be improved, and I've got some idea how to improve it myself, but this is not the part of this presentation. That's it. Questions? Yes. Yes, yeah, I believe so. But even if it's not centered very well, it's still going to work. But of course you have to calibrate the distance to one particular angle. So it's supposed to be pretty precisely pointed. Yes.
How accurately are you able to estimate the power consumption of your chip with software?
Very accurate. Let me show. So actually, it's those 2, 4, 9. Those are not nanoseconds. Those are amount of the steps I have to do. I mean, an amount of operations I have to do the calculations. So and I know the cost of every step, and the cost of every operation is 7 or 9 picojoules. So this estimation is very accurate. And I kind of like this kind of approach. So I can tell the cost, I mean energy cost of every operation. So you can think about what's good and what's bad. So you just when you're deciding which module or which solution you're gonna apply or you're gonna combine together, you can estimate the cost, the energy cost of each combination of each particular decision. So from the point of the green design oriented to the power efficiency, this kind of environment and this kind of chip is perfect.
So my question is, if you measured 80 milliwatts, what did you calculate?
But I'd say 5%, plus minus 5%. Because I remember when I sent, because I never saw personally the hardware implemented, only on the picture, because we just communicate with the email, and they've got I believe the same power consumption than I estimated. Probably 5% less. Yes. Probably not. Well, the thing is, these nodes are pretty busy. I couldn't find any gaps or any. So this is pretty optimized application. And the thing is, these nodes are not 30% loaded. It's closer to 70%. And the 30% result of these unloaded nodes. And the interesting thing about these 5.0 nodes, they run 100% on port. They don't use RAM for the code itself, because they really need this RAM space for the data So that's why we decided to run all the code on the ports. So they're sleeping on the ports, and then every node have a couple of instructions on a data stack. So every time I have to bypass data from this node to this node, I send the instruction to this node to execute it on port, and then I provide it with the data. And then this node will do the same thing to his right neighbor. Send the code to execute and send the data to feed this code. It's going to be executed. So this is very unusual. I mean, it's very usual for this architecture technique, but from the general point of view, it's very unusual technique to send the code to execute on port. So it's yes, sorry.
On the output of the chip, we see what appears to be very similar to a key graph, where things that are closer are brighter, things
Yes.
that are more distant are dark. In the equations for the SAD algorithm, you had a variable k that indicated an offset. Is this just a graph of that k value?
Yes. And the thing is, if you've got if you've got several minimums for with a different case, we decided to choose the remoted version because it could be well this is the way what is done in the non-implementation. So basically I haven't invented the algorithm itself. It's a very well-known algorithm. The interesting point is, a long time ago, you guys remember, probably some of them remember connection machine. Connection, with the N-cube architecture. So this algorithm, SSD algorithm, was one of the super applications for that connection machine. Of course, it was a long time ago, and these days my cell phone is much more powerful than the Cray. But it's very interesting, history fact. Okay. Hmm? Oh, this is the local storage for the pixels, because you've got the stream of pixels, the line coming, but to calculate the difference, you have to use two previously streamed line of the pixels. So one time you have to have 3 lines from the left and 3 lines from the right. So basically this is the local storage. And if I had to increase the resolution of the screen, because right now it's 384 by 288, I probably will need bigger array. 40 cores is not enough for the high resolutions. Yes. Yes. Okay. Yeah. Well, I say indefinitely. Well, the only thing is probably right now the input is just scanning the line by line, and if I based on my current understanding how to implement the thing, because I'm explaining to you, the thing I already know how to do it. So probably there's some alternative version. But anyway, so if I could scan multiple lines from the input frames, not just line by line, but probably the 2 lines in parallel, or 4 lines in parallel this way, I could increase the performance with using more SAD nodes running in parallel. Yes. Yes. I don't know. I honestly don't know. Just a robot, Well, in theory, it's kind of robot, which is supposed to patch the. You remember the issue with the spilled oil in a Mexican Gulf? This kind of robot, which understand, the environment, and they could do this kind of job. Sorry?
Some
No. Well, probably they have to well, well, actually, well, this was just one particular example how low power consumption of this robot is. So it's low enough to survive on the sun cell. But you can replace this cell with the small lithium battery. So it's not the important part of the design. The sun cell.
One more question.
Yes.
To get a stereoscopic effect, you want not to orient each camera straight ahead rather than converging on a particular distance. To get stereo separation, you want to keep them straight ahead. Well, it's best where you converge. Yes. Yes. All right. Well, that is where you converge. You're probably thinking bigger pyramid. No, I'm thinking that if I'm looking straight ahead, then the difference in displacement of each image. Well, that gives you not looking straight ahead. Yeah, because when I look at my finger here, my eyes are like this. Right. See, this is why since I lack stereoscopic vision, I don't know how it works. So I just want to know. So what you got to know.
Well, probably this is the part of how we see. I think our stereoscopic vision, processing the stereoscopic vision, way more complicated than this one. This is just one simple particular algorithm our brain may use to. Okay, I think I took too long time.